Okay guys, so what we're going to be talking about today, as you can see here, is average rate of change. Now when we talk about average rate of change, the type of average rate of change that most people are familiar with is when you see something like this. Like let's say we watch this car, and I know this is not to scale, but let's say we watch this car travel 180 miles down the road. So car goes down the road, accidentally hits that dude, he's totally fine, I promise. And it took 3 seconds to travel those 180 meters. Now, most people, when you ask them the question, how fast was the car going, what was the speed of the car, you would immediately say, oh, that's 180 meters, because that's how far it went, divided by 3 seconds, because that's how long it took, and we would say in this case that that would be 60 meters per second. And I think everybody agrees that that is more or less how you find the speed of a car. More in general, anytime, and it doesn't have to be meters and seconds, but anytime we talk about defining a rate of change, which is what a speed is, that involves distance and time, we always say the total distance traveled divided by the time elapsed, and that will tell us how fast we are going. Okay, and that's what we've always learned speed to be, or sometimes it's called velocity. We'll talk more about that later. Okay? Now, the reason why this could be slightly misleading is if we go back and we think about what that car did, it sped up and then it slowed down. So technically, even though we found its speed to be 60 meters per second, that wasn't how fast the car was going the entire time. What we found instead is not the actual speed of the car, we found the average speed of a car. Okay? And I know that doesn't seem like it's a big deal, but in reality, when we say how fast are you going, like if you're driving in your car and somebody calls you and says how fast are you going, you don't get out your calculator and like, okay, well I got to figure out how far I went from when I started and how long it took, then divide the two. Instead, you just look at your speedometer and at that moment it tells you how fast you are going. So keep that idea in mind as we move forward in this class, because there will be a time when we have to talk about that a little bit more, and I want to make sure that we're all on the same page. Now, more specifically, when we talk about average rate of change in this class, it's a slightly different scenario, because not only are we looking at real life scenarios like the first one we looked at where we just do time, distance divided by time, but we can look at this in a slightly more general sense. One way that we can kind of say what's happening in these problems is we can say what an average rate of change is a total change in the dependent variable divided by the total change in the independent variable. Or you could say the independent variable, what we talk about that being for the most part is our x values. That kind of relates back to time if we're talking about our original equation that we looked at. And then our dependent variable in general is usually y. That's the distance that's been traveled. But because we won't always be talking about distance and time and something a little bit more specific, that is what our dependent variable is. It's like our y value. Okay? So, when we look at a function, like this one right here, for example, we have this parabola. The equation of this function is y equals 3x minus 2. And I ask you about the rate of change of a function like this. It's a slightly different scenario. When we look at this scenario, what is happening is we're saying, okay, there's no like real life application to apply it to. And so what we're looking at here is we're saying, okay, I'm looking at this function. Now, this is written incorrectly. These should be brackets here. So I apologize. Both of these should be brackets. And in all the problems when we're talking about intervals, those should be brackets as well. So what this is saying, we're not going to talk about exactly how to find it yet, but what this is saying is I want to find 2 different points on this function. The first point is going to be when x equals -1. The second point is going to be when x equals 0. And what I want to find, and this is what it's saying in a problem like this, is I want to find the slope of this line that connects those 2 points together. Now this line has a special name. This is what is known as, you can see here, this is what is known as a secant line. A secant line is simply a line that connects 2 points together on a function. Okay, so in this case, what I'd be looking for the average rate of change is the slope of the secant line from x equals -1 to x equals 0. Now, luckily for us, there is a formula that we can use to find the average rate of change anytime we have a function, whether or not we have a picture like we did over here, or in general. The simplest version of this form is those little triangles, we call those delta, so this is delta y over delta x. Delta always means change, so this is saying find the change in y on that interval over the change in x. A better way to write that formula, especially for us, is to say it more like this. Now, I know that looks a little bit confusing, but on the bottom, all we have here are these are the two x values that we were given. So that x2 and x1, it doesn't matter which one is which, that's totally fine. On top, what we have are the two different function values, or the y values, that go with those x values. And then this just becomes our slope formula again. y2 minus y1 over x2 minus x1. So if we go back to our problem that we have here, and I want to find the average rate of change, again, those are brackets, on this interval, what that's saying is that it wants me to... So when we look at this, well, again, what I want is, we know what we're looking for already. I want the slope between those 2 points. So really all I need, I've got -1 as one of my x values. I've got 0 as my other x value. I need to find the y values that are associated with those. If you remember, our function is 3x squared minus 2. So in this case, I would just take, to find the y value, just like we did before, I would take my -1 and I would plug that in for x, so I get 3 times -1 squared minus 2 gives me a positive 1. So I know the point -1, positive 1 is on this function. If I were to take 0 and do the same thing, I would get -2 as my y value. Then I have the x and the y value associated with, or excuse me, I have the y value associated with the x values that I was looking at, so that I can just find my slope, -2 minus 1 over 0 minus -1, which in this case would give me -3 over 1. So the slope of that secant line that connects those two points together, I can't draw a straight line, but other than that, connects those 2 points together, the slope of that line is -3. That also represents the rate of change of this function on that interval. So that's the idea behind average rate of change. Let's do a couple of examples, knowing actually, when you think about this, you actually don't have to draw you don't have to know what the graph of the function looks like, because all I need is the x values and the y values, and I'm given the x values already, so I just need to find the y values instead and just use this formula that we're talking about. Okay, so let's do this example. I think we'll do one more and then we'll call it. Actually, I think we're just going to do this one and we'll finish the video off. So if I had this function, notice I'm looking at the interval from -1 to 4. So I know my x values are -1 and positive 4, and I just want to find the y values that go with them, so that I can I'm going to try and change the pen color here. It'll let me do that. Okay, so I've got -1 and 4, and I want to find the y value that goes with those. Okay, so for -1, I would just take -1 and I would plug that in everywhere I see an x, because I need the y value in order to find the slope between these 2 points on the graph. So I get -3 minus 2 is -5 plus 1 is -4. So my first point is -1, -4. Then I take 4, oops, it's cubed, not squared, it still gives me the same answer. So then I get 3 times 4 to the third plus 2 times 4 plus 1. Well, let's see, 4 to the third is 64 times 3 is 192. Plus 8 plus 1 gives me 201 for my y value on that one. Again, if we were to graph that, that would actually be very difficult to see, at least initially, on a calculator. So now I just apply my formula, because the average rate of change is telling me I'm finding the slope between these 2 points. So I go 201 minus -4 over 4 minus -1. 201 minus -4 is 205. 4 minus -1 is 5. So the slope of the line that connects these 2 points together would be 41. Another name for that slope again, or that line, is the secant line. So the slope of the secant line in this case would be 41, which also represents the average rate of change of this function. Hopefully that makes sense, and this idea of finding the slope of the secant line, we're going to build on it soon enough. It will help us in the future, especially with a lot of calculus. Even though this seems kind of pointless right now, eventually this will help us in a lot of different ways. So hopefully all of that made sense. If you have any other questions, please come on in and I will answer them.